Now by minimizing that risk function, that is R is equal to B mean square error theta hat. And now obtained from solving this one. Optimum coefficient An. So An is a expression of theta minus An expectation of Xn. So go to previous expression, substitute. So this is theta minus theta hat square. So substitute this theta, this one. So expectation of this. So minimizing this one. So differentiating with respect to that. So take expectation summation operators exchange. So this is, so it is expectation of theta minus A transpose expectation of Xn. So E of X. So dot product computation. So A vector is multiplied with E of X. E of X is expectation. It is a number. So it is expectation of theta minus A transpose or A multiplied with A. How do you compute? It is Cxx inverse Cx theta. Or Cx theta by Cxx. What is Cx theta? Covariance of your observed data vector with your original parameter estimator. Denominator Cx of X. The covariance of X with X is nothing but variance. That is sigma X squared. If it is A plus Wn, sigma X square is equal to sigma A square plus sigma W square. Sigma A square, if at DC level is 0, so it is nothing but sigma W square, it is sigma square. So Cxx inverse for your DC level case is simply 1 by sigma square. So that this computation Cx theta may be in terms of your sigma square n value. So therefore the value of A is depending on n also. So hence typically this is the equation to represent the value of linear minimum mean squared error estimator. Expectation of theta plus C, substitute A plus X minus Ex. So what is this minimum value? Minimum value try to find. So it is C theta theta minus C theta X, Cxx inverse Cx theta. So there's some 1 or 2 steps are there in between. I have not considered them. If you go through them, you can easily understand how this is reduced minimization. Minimum value of this one. How do you find minimum value of this function? Again, try to differentiate and make it equal to 0 and solve that one. Okay, so expectation of theta is constant. So derivative of that with respect to theta must be 0. So first one will go away. Second one will come out now. Expectation of X minimization. I mean with respect to theta, if you take theta plus Wn. So therefore that theta X Cxx inverse into the expectation of first one is dou theta by theta is 1. So this is this one. And other one is Cx theta. So theta X, Cxx inverse and Cx theta. So this is how the minimized function will lead to this value. And please see right hand side is always covariance computation. So that is simplicity. So first one is covariance of your parameter. Second one is covariance of parameter with respect to X. Second one is covariance inverse value of data itself. And this is covariance of data. So that means Cx theta and C theta X, usually same. So let us see this computation for a famous example we saw earlier, so that you can easily understand these computations. Formulas are same, algorithm is simple. Okay, so therefore take the example DC level in white Gaussian noise with uniform PDF. That means the parameter will have uniform density function. So therefore, observed data is x of n, a plus wn. So wn is white Gaussian noise with variance. Therefore, noise is assumed to be normal with zero mean, and sigma w square, sigma square. So unless specified sigma square, whenever you see it is nothing but sigma w square. And A is a uniform PDF. It is assumed with zero mean. Okay, please see A is a zero mean, and it will be defined between minus a naught and plus a naught. So it is uniform density from the parameter value minus a naught to plus a naught. It's a bidirectional two-sided uh, rectangular function or square function minus a naught to plus a naught. So what is the height of your density function for a now? 1 by 2 a naught. You can plot it. So if you plot it in examination, if it is also first to plot the two PDFs for your clarity. So if you see now, both are centered around 0 because noise also is 0, but it has its own variance. This also is PDF. What is the variance now? It is minus a naught to plus a naught. So the variance of noise and variance of a parameter are not same, but both are centered. Both have say this mean value 0. Okay, hence they are centered around that one. So draw that single plot, one rectangular square function, uh, and one Gaussian function centered at 0 origin. Okay. Now the unknown parameter theta, that is a, must be estimated. So therefore, if you want to estimate linear mean squared minimum mean squared error estimator, it was difficult. We could not obtain it closely. See that example. Now go for linear minimum mean squared error estimator. And now you apply the computation of this one using this formula. So what is expectation of a? Expectation of theta. Want to compute. So first term, if you take expectation of a is 0. Why? Because it's uniform from minus a naught to plus a naught. So mean value is 0. So therefore, what happened to expectation of a equal to 0? So what is expectation of x? Expectation of a plus expectation of wn. And what is the expectation wn? It is also 0 because 0 mean. Therefore, expectation of x is 0. Is this clear? Okay. So now what about covariance? Because expectation of x is 0, what is the covariance definition? It is a covariance between x minus expectation of x, theta minus expectation of theta. That is the covariance definition. So if it is C of x, it is expectation of x minus expectation of x multiplied with expectation of transpose of x minus E of x. So it is expectation of x transpose because mean are zeros, both are. So it leads to expectation of a plus wn multiplied with a plus wn transpose. So expand all of them, and the expectation of a and expectation wn is 0 because they are not depending on each other, independent. But a square will be there, and the expectation of wn square will be there. That is sigma square. So it is expectation of a square. Of course, 1 transfer. This is a lot of rather matrix multiplications, sigma square I. So there similarly compute C theta of x. What is C theta of x? Expectation of theta minus theta average. Expectation of theta into expectation x minus expectation of E of x in the bracket. X minus E of x. So now expand all of them, multiply, and expectation of theta, that is a and x again independent, that is 0. So it becomes expectation of a square. So theta x. So substitute into your, where is that definition? This one. So C theta x, Cxx inverse you computed, x minus Ex. But E of x already you have seen 0. So it is expect x. So this is C theta x, Cxx inverse x. So substituting that x. So substitute is sigma square plus sigma square inverse. So that is how Sigma A square, what is sigma A square? Expectation of A square. Expectation of A is A. So therefore, sigma square is expectation of A square, and it will be equal to A square, and mu A was 0 because it was a two-sided uniform density function. Therefore, this value simply becomes sigma A square divided by sigma A square plus sigma square by n x bar. So hence for uniform PDF, this is equal to expected A square. For uniform density function, it was del square by 12. So what is del 2 A naught? So A naught square by 3. So therefore variance is A naught square by 3. So substitute here A naught square by 3 by A naught square 3 plus sigma square by n x bar. So of course this x bar is a summation of x with 1 by n. Okay, this n goes there and gets cancels that. So this is how linear minimum mean squared error for your parameter with a uniform density function is this term. Why is this example so important for us? Because already I have justified many times the analogy you try to pick up for RF sampling. So envelope of your digital modulated symbols is constant. Within the symbol it is a sinusoid. Therefore, if you take midpoint sampling and decide the symbol whether it is 0 or 1, you may get errors. That is why today you will use multiple samples in the bands in that single symbol interval. So 100 sample, 1000 sample, depending on your switch sampling possibilities. Because of course you have to apply the band pass sampling theorem. Not difficult. You can find out the value sampling proper sampling rate. So that RF samples of same symbol are now averaged usually. So that is why all estimators will use averages. That average value is now compared. So think of matched filter. Okay, that average value is sample. Now that is compared. Earlier, you took an incoming sample, midpoint sample, one sample value, and switch will give you that sample value. So a matched filter detector was using one sample only, but now you replace that with a Wiener filter. So you will get this linear mean square error estimator, which minimizes the mean square error, base risk, and also linear, easy to compute. Because A naught is known to you, sigma square is known to you, n is you are choosing it. So x is observed data, you can compute it. So A naught is constant, x bar is constant after computation. N is constant, sigma square is constant. So A bar can be easily calculated. So this is how estimator of A is simply some computer where you have x bar, that structure I am explaining. So physically you can put a block diagram to implement a LMMSE. What is that one? First you compute x bar, that is average. So xn is the input data, n samples are going in, and you are taking the average of that. So one adder, one multiplier with 1 by n gain, okay, second input, or branch coefficient 1 by n. And now that goes into a multiplier. What is that multiplier? Another input, this coefficient a naught square by 3 divided by a naught square by 3 plus sigma square by n. So you can take it as some twiddle factor already computed, fetch it and multiply it. Now you get the estimate. Output is estimate. This is how practically you implement a linear minimum mean squared error estimator. So what is the hardware complexity, computational complexity? You need one average computer and one multiplier. Is it not a simple implementation? So that averaging is done by simple adder and one multiplier. Of course, if you use Wiener filter, you can use adaptively to change that value so that the value of A hat is close to A, your true value. If it is ASK with minus A naught and plus A naught as two valid levels, the value of A could be either plus A naught or minus A naught. That means X bar must be converging to either plus A naught or minus A naught. If it is a polar signaling. bipolar signal, like PSK. PSK also has two amplitudes, plus A naught and minus A naught. Is this clear to all of you? So if you understand this example carefully, so it's so simple to implement your demodulators. They are nothing but estimators. And these mathematical equations which you saw here are converging or converting into simple computations of additions and multiplications. So your algorithm will use these values, compute them a priori. Because A naught is known a priori. Truth table for QPSK is known to you, or a PSK is known to you. Sigma square is known to you, because noise Wn, you know, it is Gaussian with certain power, noise power n naught by 2. N is known to you, number of samples you are fixing for every packet, or for every RF sample, the value of n can be chosen, 10, 100, something. So that is why today there is no midpoint sampling concept. It is average sample averaging concept only. So it's a very important point you need to know, especially when you are processing digital modulated signals, wireless or wired, baseband or baseband. Is this clear? So I want you to read once again. Give her one or two readings, so easy to understand these mathematical equations and the corresponding derivations. Finally, the final form of these estimators coming to very simple forms, so that you can easily implement that. So hence, linear minimum mean squared error estimator is not unbiased. It is not satisfying because A hat is not equal to A. It will be equal to A only when the value of n is very, very, very high. So that that A naught square by 3 and A naught square by 3 gets insignificant, gets cancelled out. So it will be n by sigma square x bar, and x bar is sigma square by n. So both will be n A square by sigma square. So it is sigma square by n A. So therefore sigma square by n, sigma square by n gets cancelled, and you get A right hand side. That's what I am explaining uh, clearly, so that it becomes unbiased only when under one condition, that is the value of n very, very, very high, asymptotically unbiased. That is why it is not optimum, because a hat is not equal to A even for smaller n. N should be very, very high. That is why RF sampling today is not midpoint sampling. It is not. It has drifted away from midpoint sampling, and you have RF sampling coming into picture. So that band pass sampler is implemented prior to your estimator. So the input data which you are assuming x0, x1, xn minus 1 are actually coming from sampled RF pulse. They are now sampled RF pulses. Incoming analog digital modulated signal is sampled first using RF sampling, band pass sampling. Those samples we are assuming as input to your detectors or estimators. Hope I clearly justified this estimation and detection concepts with your digital communication aspects. Easy to understand. With this, I am stopping here today. So in the next class, I will go to Wiener filters. So again, I want all of you to go through from first chapter to till the last this chapter, linear minimum mean squared error estimators, so that those concepts, if you understand thoroughly, Then Wiener and Kalman are easy to understand. You can easily apply them. Okay, right.